Imagine an object with gravity so absolute, every path on its surface leads inward. It swallows light itself. For decades, physics operated on a simple assumption. Once a black hole formed, it was permanent, a cosmic vault that would sit in the darkness forever, consuming whatever crossed its path. But that raises a massive physical contradiction. If an object is defined by its ability to trap absolutely everything, can it ever lose mass? Can a black hole shrink and eventually die? You won't find the answer by looking at giant stars or massive galaxies. To understand how a black hole dies, you have to completely abandon the macro universe and look at the invisible, microscopic fabric of space. In the 1970s, a young physicist named Stephen Hawking presented a mathematical proposition that baffled his peers. He argued that black holes are not completely black. Instead, they emit a faint, steady stream of radiation. To see how an inescapable gravity well can push radiation out into space, we have to look at the highly counterintuitive rules of quantum mechanics. Start with a deeply strange premise. In quantum physics, a complete vacuum, a totally empty region of space, is never actually entirely empty. Even in the deepest void, virtual particles and antiparticles spontaneously generate. Space constantly bubbles with this activity. Under normal conditions, they exist for a fraction of a second. They pop in, instantly collide, and annihilate without a trace. Because they cancel each other out so fast, this constant bubbling goes completely unnoticed everywhere in the universe. Unless, of course, a pair happens to spawn right on the edge of a massive gravitational field. Around every black hole is the event horizon. This is the precise mathematical boundary marking the point of no return. Now, picture one of those virtual particle pairs popping into existence right across that line. The gravity here is extreme enough to rip the pair apart before they have a chance to collide. The particle inside the boundary gets dragged down into the black hole, but the particle just outside the boundary shoots free into space. To anyone observing from a safe distance, that escaping microscopic particle looks like a tiny emission. The black hole is radiating energy. If a particle escapes carrying energy, that energy has to come from somewhere. The laws of physics dictate that you cannot create energy from nothing. Me-energy comes from the black hole itself. Thanks to Albert Einstein's famous equation equating energy with mass, we know the two are directly connected. This chart shows the mass of a black hole over a massive timescale. Every single time a particle escapes, it carries away a minuscule fraction of mass. Over trillions of years, the giant slowly shrinks. As a black hole loses mass, it actually starts bleeding energy faster. A smaller black hole radiates more efficiently, which causes it to lose mass even faster, creating a runaway effect. For the vast majority of its life, the decay is impossibly slow, but in its final moments, the process accelerates into a furiously hot, intense burn. The most powerful gravitational structure in the universe is taken apart piece by subatomic particles. It ends in a sudden, blinding flash of radiation, leaving absolutely no remnant behind. The physical structure is gone, but its disappearance creates a massive problem for physicists. Over its lifespan, a black hole swallows entire stars, planets, and countless tons of matter. If the black hole completely vanishes, what happens to all that physical data? Quantum mechanics operates on a strict rule. The core information that makes up the universe cannot be destroyed. We still do not know if that information is somehow preserved in the escaping radiation, or if it is entirely erased. It remains an intense, unsolved puzzle driving modern physics forward today. Fast forward far into the deep future of the cosmos. Trillions of years after the last stars have burned out, and the galaxies have faded to black. The universe becomes a cold, dark expanse. Eventually, even the most formidable, inescapable gravitational giants quietly evaporate away into empty space. Given enough time, nothing survives. This ultimate impermanence is a built-in feature of reality itself.